Lesson 5.2.1, Investigating Properties of Dilations. Our objectives: what are the four properties of dilations? What is a scale factor? How do I use it to determine if a dilation is an enlargement, reduction, or if it's congruent? And what additional notation do I need to communicate about dilations? So here's our vocabulary. So a dilation is a transformation in which a figure is either reduced or enlarged by a scale factor. So imagine if, let's say Honey, I Shrunk the Kids. Hopefully you guys can relate to this. It's not too far out of your guys' time period. So Honey, I Shrunk the Kids, the father makes a shrink ray and shrinks his children. Now this shrink is considered a dilation, so it's a reduction. So they're reduced. They maintain their same shape, so they're the same exact proportion, but they're smaller. Okay, so that's what we're looking at when we're talking about dilations. It's taking an image, enlarging it by the same proportion, or reducing it by the same proportion. Scale factor. Now the scale factor is going to be the amount that it is enlarged by. So let's say you take a piece of paper and you enlarge it by 2. So your scale factor is going to be 2. Or if you triple the size, then your scale factor is going to be 3. Okay, so now an enlargement, so this relates to scale factor. So an enlargement is when you have your scale factor greater than 1, and sometimes it's notated by k is greater than 1. Okay, and that tells you how much larger it is. So it can't be 1. It's not greater than and equal to. It's just greater than 1. So 1.1, 1.2, 1.3, and on. You're looking at an enlargement. A reduction is when k is less than 1. Okay, and of course it can't be 0. It can't be 0 or less than 0. And congruence, right? That means nothing changes. Scale factor is the same. Is when k is equal to exactly 1. Okay, prereqs. So the properties of dilations. So 1, the shape, orientation, and angles all have been preserved. And let me just go ahead and draw an image here. All side changes by a single factor of k. The corresponding pre-image and image sides are parallel, and the corresponding points of a figure are collinear with the center of dilation. So what that means is, let me draw a house here. So here's my house. It's not going to be the most perfect house because I'm not good at drawing. Okay, there's my house. So now, scale factor. Let's see, I'm going to draw I'm not going to know what the scale factor is because I'm just pre-handing this, but imagine that the shape, right, so it stays the same exact shape. I'm trying to draw this as close as I can. Okay, so the shapes of the houses stay the same. The orientation of the house, right? The house didn't move in any way, right? The roof is where the roof is. The door is where the door is. I know I didn't draw a door. And all the angles have been preserved. So all these angles stay the same. Okay, 3, the corresponding pre-image and image sides are parallel. So we're looking at this side being parallel to here. This is parallel to this. All these sides are parallel. Okay. And number 4, the corresponding points of the figures are collinear. So points just means that these here line up on that line, on this line here. For that middle line, all these points line up. And on this line here, all these 4 points add up here. It just means that they share the same line, the green line that I drew. Okay, example. Verify the shape, orientation, and angles have been preserved from the pre-image. So let's look at the shape. So we're looking at a triangle here and a bigger triangle here. So if we're looking at the shapes look to be preserved, right? They haven't twisted, they haven't flipped or anything. They're both triangles and they look like they're the same. Now, orientation, that's where it doesn't move or flip or rotate. That's the same. And the angles have been preserved. So the angles, you would actually use a protractor to see if those angles are the same for those two triangles. These two angles are the same for these two triangles. And these angles are the same for these triangles. So that's how you would see if the preserved images, if the angles are preserved. Okay, number 2, verify that the corresponding sides are parallel. Okay, so now, for the corresponding sides to be parallel, the slopes have to be the same. Slopes, same. Okay, so that means that the slope of A and B have to be the same as the slope of A prime, B prime. So if we're looking at those slopes there, remember slope is rise over run, and you always want to start on the left-hand side. So let's go from A to B. Right, we're just looking at the slope of A to B. That is up 1 over 1, 2, 3, 4. So up 1 over 4. Now let's look at A prime, B prime. We're up 1, up 2. And we're over 1, 2, 3, 4, 5, 6, 7, 8. And if we reduce that down, that's 1/4. Okay, so far, that side is parallel. We got to check all the sides, and we could just freehand that real quick. So C is up 1, 2, 3, 4 over 1. 4 over 1. From C prime, 1, 2, 3, 4, 5, 6, 7, 8 over 2, and 8 divided by 2 is 4. So those two sides are parallel. And then the third one, we can check that really quick. From A, so we're going from A to C, that's down 1, 2, 3 over 3, 1, 2, 3. So that's -1. And then 1, 2, 3, 4, 5, 6, and then over 1, 2, 3, 4, 5, 6. That's also -1, right? It's down 6 over 6, 6 divided by 6. Okay, so that's check. So they did have parallel sides. Okay, now number 3, verify that the distances of the corresponding sides have changed by a common factor. All right, so let's do 3. Remember, distance, we have to pull out the distance formula. So distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared. Oh no. Oops. Let's see if I can do this. I can't get the square in there. No. Struggle's real right now. There we go. Okay, so there's our distance formula. So I'm going to first do it for AB. So you want to find all these distances here. So I'm going to do AB first. So I want to find the distance from here to here. Then I'm going to find the distance from A prime to B prime. After we do those, we're going to find B to C, and then B prime to C prime, and then last C to A, and then out here C prime to A prime. Okay, do it on the side just because they're going to overlap. Okay, so let's do A to B, and then we'll start filling these in. So we've got to find the coordinates. This is -2, 2. And B is at 2, 3. And I'm going to label these x1, y1, x2, y2. And I'm going to plug it into the formula. Right, this should all be reviewed to us. So x2 is 2, minus x1 is -2. That gives me the double negative there. Plus y2 is 3, minus y1 is 2. And we can simplify. So 2 minus oops, sorry, we got to do, I forgot one parenthesis here. Okay. So inside the parentheses first, we got to do 2 minus negative 2. That gives us 4. That's going to be squared. Plus 3 minus 2 is 1. And that's going to be squared. And then just simplifying, 4 squared is 8 plus 1. Oops, sorry, 4 squared is not 8. 4 squared is 16 plus 1. 1 squared is 1. Then now we have the square root of 17. And if we grab our calculators and we put in the square root of 17, we get 4.1213. Okay, so I'm going to plug in 4.1213. Okay, so now we got to do the distance formula for all the rest of these, but I'm going to go ahead and I've worked them out already, so I'm going to just throw them into the video. So I'm going to erase all of this so it gets a little more clear. Okay, so for A, we looked at 4.1213. So here is 4.1213. A prime to B prime is 8.2462. Right, and I only know these numbers because I have already worked these out. Let's see, B to C is 4.1213 as well. B prime to C prime is 8.2. Uh-oh, how'd the color change? 8.2462. And now A to C is 4.2426. And then this long one here from A prime to C prime is 8.4853. Okay. So now we can find our scale factor, and we find our scale factor by determining how much bigger this image got, right? So we started out with this image here, triangle ABC, and we got to this triangle here. So how much bigger did it get? So what we're going to do is we're going to take the big sides for the bigger triangle. So let's say I want to do the red side first. I'm going to do 8.2462 and divide it by 4.1213. So 8.2462 divided by 4.1213. And that gives me a scale factor of 2. There's a little decimals behind it, but we'll just do 2 just because the numbers are fairly close. Okay, the other side, so the blue side, we're going to do the same thing. And it's the same numbers, so you're going to end up with the same outcome. That's equal to 2. And the last side, we got 8.4853 divided by 4.2426. 8.4853 divided by 4.2426. And that also gives us 2. Okay, so now that all 3 of the sides have the same scale factor of 2, we can say that the scale factor is 2. Okay, and that's verified. And the last one here, the collinear part. So collinear starts from the, let's do this in green. Okay, collinear starts from the point of dilation. So where we have, right here where we have it, D. That's our point of dilation, or center of dilation. So from this point, what it's saying is that if we draw a line, A and A prime should be on the same line. So if I draw a line from the center of dilation going through A and A prime, those fall on that same line there. So if I draw a line from B to B prime, those should also fall on the same line, and see how they do. And then C and C prime, they fall on the same line. So those are collinear. Yep. So all the ways to verify dilations. Okay, now this one. Determine if a transformation is dilation. So if I'm looking at the shapes, it looks like I have a right triangle here and I have a right triangle here. So far it might be a dilation. Orientation, I got a straight side, straight side, straight side, straight side, and I have a hypotenuse. The hypotenuses match up. It's on the same side, it's on the same position. So still might be a dilation. And then angles, of course, we can't. I don't have a protractor tool here, but you can always use a protractor to check the angles. We at least know that these both are 90. These you would have to use a protractor to check and see what these are. Okay, and remember the angles have to be the same. Okay, now we can go down here to step 2 where it says verify that the corresponding sides are parallel. So corresponding sides are parallel. Remember they have the same slope, but we can already see that this side is parallel to this side, right? They have the same slope there, right? They have a slope of up 1, up 2, run nothing, right? They have a slope of 0. Here, this is parallel to this, so far we're good. All the sides are parallel, right? They have the same slope there. The slope here is 1, 2, 3. Well, they're parallel. Okay. Now, this line here, we can figure out what this slope is, right? It's just the rise over run. So if I do the rise over run from C to B, I'm looking at down 1, down 2, down 3, down. Let me erase all this. Okay, so I'm looking for the slope of this line here in purple. So that slope is down 1, 2, 3, 4 over 1, 2, 3, 4. So down 4 over 4. Okay. Now I want to find the slope of the hypotenuse for the next one. That's this one here. This slope is down 1, down 2, over 1, 2, 3. And if we simplify these out, these do not equal one another. They are not the same. So we can say the hypotenuse is not similar. Not similar, sorry, parallel. Which means that these two triangles are not similar. Okay, it didn't pass the parallel test. And chances are, if we had a protractor and checked the angle measures, it wouldn't have passed the angle measure test either, where all the angles have to be the same. These angles would have been different. The purples and the reds would have been different. Okay, and then verifying distances. So just to do a quick one, anytime we're given something that's exactly on the axis, use it. It makes life so much easier. So if I look at the distance here, that's 1, 2, 3, 4. That's given to us right off the bat. That's 4. This one here is 2. Now if I look at this one here, that distance is also 4. And if I look at this one here, the distance is 3. So now if I compare these two, I have 4 over 2. And then we have 4 over 3. 4 over 2 reduces to 2. 4 over 3 doesn't reduce. These do not match up. So does not have a common scale factor. So no common scale factor. K means scale factor. And then verify that the corresponding sides are collinear. It doesn't look like it gives us the point of dilation here. But remember, there would be, it's the origin. So those points there are on, let me get A prime a little closer. Those points there are, and then if we look at B to B prime, those miss. They're not collinear. So that's another way to check to see that is to prove that these are not. So it would have to been right there where it would match up. So B is a little off. Okay, do the following transformation represent a dilation? What is the scale factor? And does this indicate enlargement, reduction, or congruence? Okay. Now, the rules we have here, we can verify that the shape and orientation angles have been preserved, right? So if we're looking at it, it's the same triangles. Verify that the corresponding sides are parallel. This one's a little harder because we don't have it on a grid, so we can't find the slopes of each one. Verify that the distances of the corresponding sides have changed by a common scale factor. So that we can check because we know the side measures, right? We know these are pretty much the distances that it's already given to us. So now the scale factors, we want to compare triangle to triangle. So what we're going to do is we're going to put prime on top, right? So you always want to put the new image on top, the old image on bottom, right? So this is the new image. The one with the prime is always the new image. And this is the old image. That's the one that we started with. Okay, and I'll write that here. So let's say we want to compare, let's do side A prime, B prime, to, it's going to be the old, it's going to be to A and B. Okay, so when we do this, A to A prime, B prime, and AB. Okay, A prime, B prime is 2.5 over A to B is 10. That gives us, right, you take your calculator, 2.5 divided by 10, 0.25. Okay, so now next side, we can do B prime, B prime, C prime, B prime, C prime, 2, B and C. And you don't have to write this out each time. If you can visualize it, then by all means go ahead and visualize it. So now 3.75 divided by 15 gives us 0.25. So far we're good. Common scale factor. A prime, C prime to AC, that gives us 3 over 12. And if you put that in a calculator, it matches up 0.25. Okay, so that is our scale factor. Right, so when we're looking at scale factor, we can say that the scale factor for the top there, K is equal to 0.25. Okay, now we got to state whether this is a enlargement, reduction, or congruence. So if we're looking at it, remember that this was the old image, and this one here in black is the new image. So it obviously got smaller. If this side was once 12, it went down to 3. So we are looking at a reduction. But remember the rules for, go back here, scale factor. It's a reduction if your scale factor is less than 1. Our scale factor here is 0.25. 0.25 is less than 1. Think of 0.25 as a quarter. A quarter is less than $1. This is a reduction. Now let's do the same for the triangle down below. Check to see if this is a dilation. So here's our old image. Here is our new image. Okay, old image, new image. So it looks like we can already tell right off the bat that this is an enlargement, right? Old, and now it's bigger. This side was 4, now this side is 10. So we know it's an enlargement, so we know our scale factor has to be above 1. Right? Because when your scale factor is above 1, you have an enlargement. So let's figure this out. So remember that it's new divided by old. So let's just start with P and R. So P and R is my old, P prime, R prime is my new. So my new is 10 over 4, which is equal to 2.5. Okay, let's do the rest. PQ to PQ, that's 12.5 over 5. 12.5 divided by 5 gives us 2.5. And lastly, we could do R prime Q prime to RQ. That's 7.5 over 3. That is also 2.5. So our scale factor for this one, scale factor, we confirmed it here, is consistent with all three. It's 2.5. And it's a enlargement. Enlargement, k is greater than 1. That's our explanation for it.